Well, now we've seen previously that matrices are closely connected to linear transformations, and in this chapter we're going to explore that connection more deeply. We've also seen that bases are involved in that connection, and here we'll talk quite a bit about that. All right, so the first section talks about expressing vectors in terms of bases. And here's an example, a little bit unusual. Here I'm thinking of the set of 2 by 2 matrices as a vector space. All right, so this is a vector in that vector space of 2 by 2 matrices. You don't really think of this as a vector, but it does satisfy all the vector space axioms, so we can consider it as a vector. You know, you can add these matrices, you can multiply them by a scalar, and so on. Now let's choose these 4 special matrices. Label this way: E11, E12, E21, E22. The top index indicates the row, bottom index indicates the column, and E21, for instance, is the matrix that's 0 except for the 2-1 entry. Now, any arbitrary matrix, ABCD, can be expressed as a linear combination of these 4 matrices, which we write this way, this linear combination. And we can express these coefficients, arrange them in a column vector, and write this expansion in this way. This is sort of an abuse of matrix notation. Typically, when we multiply row vector times column vector, this is a number, this is a number. But we're just doing this to show the arrangement. First component here times first component here, second component times second component, and so on. All right, so ABCD relative to this basis expressed by E1, E11, E12, E21, E22 has these coefficients ABCD. All right, so this is the standard way that we're going to represent vectors in terms of bases. Here's another very simple example. We have a basis of R2, and if we express a vector in terms of that basis, a vector xy, for instance, in terms of that basis, well, this is x times E1 plus y times E2, and we just use the same unified representation to show this, that this column vector xy represents this standard vector xy in the basis E1, E2. This is why we call E1, E2 the standard basis, because this basis representation of the vector is the same as the vector representation that we always use. Now, we can use a different basis. All right, so that's what's shown down here. If I have 2 different vectors, I can still express an arbitrary vector in R2 in terms of these 2 basis vectors. Again, we use the unified notation. xy expressed in basis B consists of the 2 vectors b and beta times xy. Okay, so we can write it this way. Now notice that xy in basis B is not going to give us the standard xy that we saw previously. For example, xy in basis B, according to the standard basis representation, would be x plus y, x minus y. All right, so there are multiple ways of expressing a vector. You have to be very specific about which basis you're expressing the vector in. So you may not have gotten that point completely, but we'll see several examples so you can understand it. For instance, we see here the vector 1, 1. In the standard basis, as we said, it just looks like 1, 1. But in this new basis, how would we express this vector? Well, 1, 1 in fact is just the vector b. Okay? So if I want to express this vector 1, 1 in terms of the basis b beta, I just take 1 times b plus 0 times beta. Right? So same vector expressed in different bases. Make sure you put the subscript to indicate which basis you're expressing the vector in. All right, let's go on and look at more examples. Here we have a hyperplane. Every element of the hyperplane can be expressed as a linear combination of these two vectors. So these two vectors, in fact, form a basis of this hyperplane. The two vectors in usual three-dimensional coordinate representation are 1, 1, 0, 0, 1, 1. Okay. So xy in this basis represents x times b1 plus y times b2, which in the standard three-dimensional representation looks like this. Okay. You can see 1 times b1 plus 1 times b2 would just be equal to 1, 2, 1. And that agrees with this representation here. Right. Now, you could reverse the order of bases, and you would get a different representation. Sorry, I should have said you could have reversed the order of the vectors in the basis, and you get a different representation. So the vector here would be kind of upside down version of the other vector. So just make sure that you specify, again, not just the vectors in the basis, but the order of the vectors in the basis. Let's go down to another example. All right, in this example, we consider a subset of the 2 by 2 complex matrices. Now, why is this a subset? Because not all matrices are included. In this subset of 2 by 2 complex matrices, the top left corner entry is the negative of the bottom right corner entry. And what that means is that it's trace-free. If you add the diagonal elements, you get 0. And it actually has a basis of 3 matrices. And we'll see that basis down here. Now you might ask, why did you choose these 3 matrices? Well, it turns out that it comes from physics. Now I mentioned that these 3 matrices form a basis for the set of trace-free 2 by 2 matrices. So let's see if we can express an arbitrary trace-free 2 by 2 matrix in terms of these 3 matrices. So let's take this V and let's verify that it is in fact trace-free. Well, if we take the sum of diagonal elements, it's 0. So this is a trace-free matrix. We want to express as a linear combination. So let's set it up. This matrix here is the matrix we want to express. And this here is a general linear combination of the 3 matrices. And we need to solve for the 3 coefficients, AX, AY, and AZ. Now, in fact, we have 4 linear equations, one for each component of the 4 by 4 matrices. Take the top left component of each matrix. That will give us one equation. For example, minus 2 plus I equals 0AX plus 0AY plus 1AZ. So that is this third equation down here. I'm not sure why they ordered them this way, but if you check each component of this matrix equation, you will find these 4 individual equations. Now, this is just an ordinary system of linear equations with 3 unknowns. Notice that these 2 equations are really the same, so it becomes 3 equations. Now, don't be thrown off by the complex coefficients. You still solve it the same way you'd solve a system with real equations. And you can come up with the 3 coefficients. And these 3 coefficients are the coefficients in the basis B that express this 2 by 2 matrix. All right, so the column vector in an ordered basis looks like this, and you can solve it by you can reduce the problem of finding the coefficients to a system of linear equations. Okay, that's it for this video.